The sunlight on your skin right now is 8 minutes old. It left the sun before you started reading this and is only just arriving. Look further out, and the delay only grows. The nearest stars show you years-old light, and the faintest galaxies show you scenes from before the Earth existed. So the night sky is not the universe as it is, but a stack of different pasts, sorted by distance. By the end of this video, you will understand how one stubborn fact, that light is fast, but not infinitely fast, quietly builds almost the entire human sense of cosmic distance, and how astronomers turned that delay from a nuisance into their deepest telescope. The strangeness is not that your sense of distance fails when you look up. The strangeness is how rarely it fails at any other time. From the moment you wake, your brain runs as a relentless and largely accurate rangefinder, assigning a distance to almost everything in view, and revising those distances many times a second without ever asking your permission. The cup is an arm's length away. The far wall is across the room. The car ahead is 3 lengths off and closing slowly. You never work these figures out consciously, yet you act on them with such confidence that you reach, pour, and break on their authority. The machinery is so good and so quiet that you forget it is running at all. It works because the world near the ground is generous with clues. Your two eyes see slightly different views of the same scene, and the brain reads the disparity between them as depth, fusing the pair into a single image with distance already built in. The muscles that turn your eyes inward to converge on a near object, and the muscles that focus the lens send their own quiet signals about how close that object must be. When you move your head, nearer things slide across your view faster than distant ones, and that difference in apparent speed, motion parallax, offers a second independent estimate. Surfaces with texture help again. The bricks in a wall, the tiles on a floor, the stalks in a field, all appear to crowd together and shrink as they recede, and the rate at which they shrink tells the brain how the ground is falling away. Objects overlap, and the one in front is plainly the nearer. Familiar things carry an expected size, so when a person or a doorway appears small, the brain reads distance rather than miniaturization. Even the air contributes, scattering light so that far hills turn pale and bluish, while near ones stay sharp and saturated. Layer all of these together and you have a sense of space so reliable that it feels less like a calculation than like a plain fact about the world. Then you look up, and one by one the clues go out. The stars are too far for stereo vision. The slight separation between your eyes, a few centimeters that resolves depth beautifully across a room, is uselessly small against distances like these, so both eyes are shown the identical flat field, and the convergence muscles relax to their limit and report nothing. Move your head and nothing shifts. Motion parallax needs a near object to slide against a far one, and here everything is equally, impossibly remote. There is no texture stretching away to be read, no receding row of objects, no overlap to say which light sits in front of which. The stars are not even disks. They are points, their true sizes far too small for the eye to resolve, so the one cue that lets you judge a familiar object by its shrinking has nothing to take hold of. The atmosphere, which paints distance across the daytime landscape, here does no more than make the points tremble. Every channel the brain depends upon returns the same answer at the same instant. No data. It is worth being precise about how completely this happens, because the failure is not gradual, but near total. The depth your two eyes extract from their disparity fades to nothing within a few tens of meters. By a few hundred meters it is gone entirely, which is why a distant mountain looks just as flat to two eyes as to one. Motion parallax reaches a little further, but it too depends on having something nearer to compare against, and above the rooftops there is nothing nearer, so the brain, denied every tool at once, falls back on the only structure left to it. It treats the whole sky as though it were the ceiling of a very large room, a single curved surface at a single distance, with the stars stuck to it like points of paint. That impression of a dome is not astronomy. It is the mind reaching for the nearest familiar shape, a ceiling, and draping the unmeasurable over it. A system built to always produce a distance now finds that it cannot. It searches for a moment, reaching for the patterns that have worked since childhood, and then it does something quietly remarkable. Rather than report a failure, it invents a category. It gathers every light in the sky into a single class and stamps them all with one label, far beyond reach, and it hangs that label, without distinction, on a star a few light years away and on a star 1,000 times more distant. To your senses, the two are identical. simply, uniformly, very far. The flatness you see, the sense that the stars are scattered across one dark ceiling at one great remove, is not a property of the stars. It is the shape of your own perception running off the end of its evidence. The night sky you experience is not a measurement of space. It is what measurement looks like when the instrument has nothing left to measure with. This is the first thing to hold clearly, because the whole story leans on it. The vastness of space is not a single fact about the universe. It is two facts pressed together. One of them belongs to the cosmos, the genuine, enormous separations between things, which are real and which we are going to measure. The other belongs to you, a perceptual system tuned across deep evolutionary time for ground you can walk, objects you can touch, and distances you can cross in an afternoon, now stretched far past the range it was ever built to cover. The feeling of vastness is what arises where those two facts meet, at the exact boundary where the eye gives up and the universe carries on. If you find these reflective explorations of the cosmos meaningful, a like or a subscribe helps us continue making them. That boundary is nothing to be ashamed of. It is simply a sign that you carry a map scaled to houses, streets, and open country, and that you use it with real skill, right up to the point where it runs out. But a map that ends at the rooftops becomes a problem the moment you want to know how far away a star actually is. Not very far, but a number, in units you could check and hand to someone else. For almost the whole of human history, nobody had that number. People had measured the size of the Earth from the angle of shadows, timed the motion of the moon, and charted the slow wandering of the planets against the fixed stars, all of it built from the cues and the geometry available close to home. The stars themselves sat on the far side of the broken map, lights on the inside of a dome at no distance anyone could name. The question, how far is that star, had no answer. Not because no one had thought to ask it, but because the senses that quietly answer every other distance question had nothing whatsoever to offer. When the answer finally came, it did not come from a sharper eye. It came from a man who understood that if perception could not reach the stars, geometry still might, that the very trick the brain plays with two eyes a few centimeters apart could be played again with two viewpoints, separated by the entire width of the Earth's orbit around the Sun. His name was Friedrich Bessel, and the measurement he made late in the 1830s was the first secure rung of a ladder that would eventually reach the edge of the observable universe. We are going to climb that ladder, rung by rung, and watch a species with senses that quit at the rooftops slowly build replacement senses out of glass, arithmetic, and stubbornness. But to see what Bessel actually achieved, and why it took until the 19th century to achieve it, we have to begin where every one of his predecessors began, with the distances close to home, the ones the human senses can still, with effort, be persuaded to measure. Begin with the nearest thing in the sky that is not the Earth itself. The moon is the easy case, because unlike a star, it is close enough to betray its distance through the very cue the night sky otherwise denies. Two observers standing far apart on the Earth's surface see the moon set against slightly different backgrounds of stars, shifted by a small angle. That shift, measured against the known distance between the two observers, gives the distance to the moon by plane triangulation, the same trick a surveyor uses to find the width of a river without crossing it. The Greeks managed a rough version of this more than 2,000 years ago, and they came back with an answer of the right order. The moon lies a few tens of Earth widths away, far enough that no journey on foot could ever be imagined to reach it. Today that distance is known not to the nearest 1,000 kilometers, but to the nearest few millimeters, and it is known because we have stopped triangulating it and started timing it. On several of the Apollo landings, astronauts left behind small panels of corner-reflecting mirrors, designed to send any incoming beam straight back the way it came. Ever since, observatories on the Earth have fired pulses of laser light at those panels and measured, with great care, how long each pulse takes to return. The moon turns out to sit, on average, about 384,000 kilometers away, and the light of the laser crosses that gap in a little over 1.25 seconds each way. This is the first solid rung of the whole ladder, and it is worth pausing on what makes it solid. The number is not inferred from how the moon looks. It is read directly off a clock, in units of the time light takes to travel, and a second is a span a human body can feel. The sun is far harder, and for most of the history of astronomy, its true distance was the single most important number that nobody could pin down. The difficulty was subtle. By the 17th century, the shape of the solar system was well understood. Kepler's laws fixed the relative distances of the planets with precision, so astronomers knew, for instance, that Mars at its nearest sits about half again as far from the Sun as the Earth does. What they did not know was the scale of the whole arrangement. They had a perfect map with no key, every distance given as a multiple of the Earth-Sun gap, and the Earth-Sun gap itself unknown. Settle that one length, the astronomical unit, and every other distance in the system would snap into place at once. The first serious attempt was ancient and ingenious and wrong. Aristarchus reasoned that when the moon is exactly half lit, the sun, moon, and Earth form a right angle at the moon. So measuring the angle between sun and moon in the sky would give the ratio of their distances. The method is sound. The measurement is brutal, because the angle is so close to 90 degrees that a tiny error throws the answer off enormously. He concluded the sun was perhaps 20 times farther than the moon. The true figure is around 400 times. The geometry had outrun the instruments, and it would keep outrunning them for 2,000 years. A first real improvement came in 1672, and it came from splitting a single observation across the width of the Earth. Giovanni Cassini stayed in Paris while a younger colleague, Jean Richer, sailed to Cayenne on the coast of South America, and on the same nights both men recorded the exact position of Mars against the background stars. Because Mars was then near its closest approach, the planet appeared in very slightly different places from the two cities, and that tiny disagreement, a parallax measured across thousands of kilometers of separation between the observers, gave the distance to Mars, and through Kepler's map, the distance to the Sun. Their answer came out within a fraction of the modern value, the first time anyone had pinned the astronomical unit to roughly the right size. It is the same logic as the moon's triangulation, simply stretched. When the senses cannot reach an object, you reach it instead with a triangle whose base is as long as you can possibly make it. The 18th century found a still cleverer route through the rare moments when Venus crosses directly in front of the Sun. Edmund Halley realized that if observers scattered across the Earth timed such a transit precisely, the small differences in when Venus appeared to touch the Sun's edge, seen from different latitudes, would reveal the Sun's distance. The transits come in pairs, separated by more than a century. So this was a measurement that demanded planning across generations. Expeditions sailed to the ends of the known world to catch the events of the 1760s. James Cook was sent to Tahiti for exactly this purpose, enduring storms, disease, and cloud at the critical hour. They returned with an answer good to a few percent, hard-won and genuinely heroic, but still soft at the edges. The clean answer waited for the middle of the 20th century and arrived the same way the moons had, by timing a signal rather than reading an appearance. In the early 1960s, several groups aimed powerful radar beams at Venus and waited for the faint echo to come back. Multiply the round-trip time by the speed of light, halve it, and you have the Earth-Venus distance directly, in kilometers, with no chain of assumptions in between. Folded together with the known shape of the orbits, this fixed the astronomical unit to better than 1 part in a million, a precision the transit observers, freezing on their distant headlands, could not have dreamed of. When Mariner 2 swept past Venus in 1962, it was navigating across a solar system whose true size had only just been settled. The Earth, it turns out, orbits at about 150 million kilometers from the Sun, and the sunlight that warms your face has spent a little over 8 minutes crossing that gap. That single sentence is the hook made literal. The 8-minute-old light is not a poetic flourish. It is a measured quantity, the astronomical unit divided by the speed of light, and it gives the Sun's distance a rhythm a person can hold. You can feel 8 minutes. You can wait through them, and in doing so you can grasp, in a way no string of kilometers allows, that the Sun you see is the Sun of 8 minutes ago, that if it were somehow switched off you would carry on in full daylight for the length of a short errand before the sky went dark. The moon at 1¼ seconds and the Sun at 8 minutes are the two rungs of the ladder that the human sense of time can still climb. They are the last distances that feel like distances rather than like abstractions. They are also, between them, the master ruler for everything that follows. With the astronomical unit fixed, the entire solar system could be laid out to scale, each planet's gap from the Sun expressed as so many of these units, and then, if you wished, as so many light minutes or light hours. The base of the great ladder of cosmic distance was now a single, carefully measured length, established by bouncing signals off a neighboring world and reading the echo off a clock. Every rung above it, to the nearest stars, to the far side of the galaxy, to the edge of the observable universe, would be built, ultimately, on this one. Pin the bottom of a ladder securely, and you can climb a long way. Leave it loose, and nothing above it can be trusted. And yet, secure as it is, this rung already sits past the edge of what you can picture. 1¼ light seconds you can almost hold. 8 light minutes you can almost hold. But 150 million kilometers collapses, the moment you try to see it, into the same hazy very large that the night sky produced. To get any real grip on the solar system, to feel the proportions rather than recite them, you have to do something to the numbers. You have to shrink the whole thing down until it fits inside a space the body knows. And the instant you do, the most striking feature of the system turns out not to be the worlds at all. It is the emptiness between them, so shrink it. Take the sun, a ball of plasma well over 1 million kilometers across, and reduce it until it is the size of a doorway you could walk through, a touch over 2 meters from edge to edge. Stand that glowing doorway at one end of a long, flat field. On this scale, where does the Earth go? Not nearby. The Earth becomes a small bead, less than 2 centimeters across, something between a pea and a marble, and you must walk it roughly 200 paces down the grass before you set it down. The moon, that companion whose distance we just measured in light seconds, is a grain beside it, circling the bead at a remove of barely half a meter. Everything in the long human story of looking at the night sky, every civilization, every war, every life, has happened on that single 2-centimeter bead, 200 paces from a model sun. Now keep walking. Mars is a smaller bead, 100 paces further on. Then the field simply empties. You walk and walk through bare grass with nothing on it, until at about 1 kilometer from the doorway, you reach Jupiter. And even Jupiter, the giant of the system, is no bigger on this scale than a small melon, a sphere you could lift in 2 hands, alone, in an enormous expanse of nothing. Saturn is another melon, smaller, 2 kilometers out. The 2 outermost major planets are beads again, set down at 4 and at 6 or 7 kilometers from the sun, each one a tiny mote adrift in a vastness of empty field. It is tempting to think there must be at least one crowded place out there. The asteroid belt, that ring of rubble between Mars and Jupiter that films like to show, as a churning hail of tumbling rocks, a pilot must weave through. The reality is the opposite, and it is the same lesson again. The belt does contain a great many bodies, but they are spread through such an enormous volume that the average distance between any 2 sizable ones is itself measured in hundreds of thousands or millions of kilometers. On the doorway scale, the belt is not a band of gravel across the field. It is a scattering of dust grains, so sparse that you could walk through it for a long time and never come within reach of one. Every probe we have sent to the outer planets has crossed the belt, and not one has had to dodge anything, because there is almost nothing to dodge. Even where the solar system gathers its leftover debris into a ring, the ring is mostly gap. If you tried to walk the whole model, the overwhelming sensation would not be of visiting worlds. It would be of crossing kilometer after kilometer of emptiness, broken now and then by a speck. This is the first hard lesson of cosmic scale, and the scale model delivers it bluntly. The solar system is not a collection of worlds with some space around them. It is an immense volume of space with a few specks of matter in it. The worlds are rounding errors. Take the proportions seriously and the planets all but vanish, while the gaps between them swell into the only thing large enough to notice. The diagrams in books quietly lie about this, and they have to, because an honest diagram would be almost entirely blank, a few dots lost on a vast white page, with the planets themselves far too small to draw at the scale of their own orbits. The familiar image of neat planets strung close together along their rings is a convenience that hides the system's true and overwhelming ingredient, which is distance. The spacecraft we send confirm the proportions in the most direct way possible, with their travel times and their silences. A probe bound for the outer planets does not take days or weeks but years, coasting along a long curved arc through that empty field, and once it leaves the inner system there is nothing for it to pass, no landmarks, no way stations, only the slow drift of the stars and the gradual shrinking of the sun behind it. The people who fly these craft have to think in a way no earthbound traveler ever does. A command sent toward a probe near Jupiter takes the better part of an hour to arrive, and its acknowledgement the better part of an hour to return. Near the most distant planets, a single round trip of conversation stretches to 8 hours or more. You cannot steer such a machine in real time. You send instructions into the gap and wait half a day to learn whether they were heard. The emptiness is not an idea out there. It is a delay the mission controllers live inside. The same emptiness shows itself in the fading of the light. Sunlight does not travel outward in a beam that stays bright. It spreads over the surface of an ever-growing sphere, and the area of that sphere climbs as the square of the distance. Double your distance from the sun, and the light arriving on each patch of you falls to a quarter. Out at Jupiter's distance, more than 5 times the Earth's, the sun delivers only about 1/27th of the warmth and brightness it pours onto us. Out at the farthest major planet, some 30 times the Earth's distance, it is down to roughly 1/900th. The sun out there is no longer a disk that rules the sky. It is the brightest star in a permanent twilight, bright enough to cast a faint shadow, far too feeble to warm anything. The light fades not because the sun weakens, but because the space it must fill keeps growing. It would be easy to read all this emptiness as a kind of failure, as though the system were mostly missing. It is the opposite. The spacing is not an absence of order, but the very thing that holds the order together. The planets ride on wide, almost circular paths that they have kept for billions of years, and they can keep them precisely because they are so far apart that their gravitational tugs on one another stay gentle. Pack worlds close and those tugs grow fierce. Orbits would be stretched, tilted, and eventually torn open, and the system would shed planets or fling them into the sun. The great distances are what keep the encounters rare and the pulls faint. The emptiness you would trudge across in the model is the same emptiness that lets the Earth trace the same quiet ellipse, year after year, steady enough for oceans to settle and life to take hold. A crowded solar system would be a violent one. The calm of ours is paid for in distance. And this turns out to be a principle that scales. The same protective spacing we are about to find between the stars themselves, and later between whole galaxies, is what lets each of them keep its structure intact. Emptiness, it will turn out again and again, is not where nothing is happening. It is the condition that lets the somethings last. And this is the system around a single ordinary star, one doorway, one field, a few specks scattered across a few kilometers of model grass. We have now measured it. The moon in light seconds, the sun in light minutes, the outer planets in light hours. All of it pinned to the astronomical unit that radar tied down to within a kilometer. The senses have been left far behind. What carries us now is geometry, timing, and the patient extension of a single measured length. But there is one more question the model is begging us to ask, and it is the question that breaks the field entirely. On this scale, with the sun as a doorway, and the Earth a pea 200 paces off, and the outermost planet a mote some 6 or 7 kilometers away, where is the next star? Not at the end of the field. Not in the next field, nor the next county. The nearest other sun, on this same model, lies tens of thousands of kilometers away, more than once around the real Earth. The gap to the stars is not the next step up from the gap between planets. It is a different order of emptiness altogether, and crossing it in measurement, rather than in travel, is exactly the leap that Friedrich Bessel was the first to make. The idea behind the leap was old, far older than Bessel. If the Earth truly swings around the sun, then a nearby star, seen from one side of that orbit and again from the other 6 months later, ought to shift its apparent position against the more distant stars behind it. It is the moon's parallax all over again, but with a colossal baseline, not the few thousand kilometers between two observers on the ground, but the full width of the Earth's orbit, some 300 million kilometers from one side to the other. Watch a near star in winter, watch it again in summer, and it should trace a tiny ellipse against the fixed background. Measure that ellipse, set it against the known width of the orbit, and a single triangle gives the distance to the star. The logic had been clear since Copernicus put the Earth in motion. The trouble was that no one could find the shift. For nearly 3 centuries after Copernicus, every attempt to detect stellar parallax failed, and the failure was so persistent that it became a weapon against the idea of a moving Earth. If we really circle the sun, the critics asked, why do the stars not sway? The honest answer, that the stars are simply so monstrously far away that the sway is too small to see, sounded, at the time, like special pleading. No one was prepared to believe the distances were that enormous. But they were. The parallax of even the nearest stars is less than a single second of arc, an angle so small it is roughly the apparent width of a small coin seen from a dozen kilometers away. To catch it, An instrument has to measure star positions to a precision finer than that, night after night, through a shivering atmosphere. Worse, larger effects lay in ambush, masquerading as the thing being hunted. In the 1720s, James Bradley set out to measure parallax, and instead found two other motions entirely. The first, stellar aberration, is a slight tilt in the apparent direction of starlight caused by the Earth's own velocity as it orbits, a real and beautiful confirmation that the Earth moves, but not the prize he was after. The second, nutation, is a small nodding wobble of the Earth's axis. Both shift a star's position by amounts larger than its parallax, and both had to be understood and stripped away before the faint, true signal underneath could be trusted. The measurement was not merely delicate, it was buried beneath other measurements that had to be solved first. It took another 100 years for telescopes, clocks, and the necessary corrections to mature. Bessel, working at Königsberg, made a shrewd bet about where to look. He ignored the brightest stars, reasoning correctly that brightness is no guide to nearness. A brilliant star might simply be a furnace seen from far off, while a dim one might be close. Instead, he chose a faint and unremarkable pair called 61 Cygni, notable for a single telling property. It slid across the sky faster than almost any other star then known. That large, proper motion was a clue, because near things appear to move more than far things, just as a passing bird crosses your view faster than a distant aircraft. If any star was close enough to show a parallax, this fast-moving one was a good wager. He trained on it a heliometer, a specialized telescope whose lens was sliced in half, so that two overlapping images could be slid against each other, and their separation read off with extraordinary fineness. Through 1837 and into 1838, month after month, Bessel followed the star's minuscule seasonal dance and subtracted away every larger effect, until what remained was a parallax of about a third of a second of arc. This was not a single triumphant observation, but a long grind of hundreds of careful readings, each one pushing against the limits of what the instrument and the night air would allow. All of them averaged and cross-checked until the tiny residual signal stood clear of the noise. From that angle, and the known width of the Earth's orbit, the distance simply fell out. The star lay roughly 10 light-years away. It is worth dwelling on what that number meant, because it is the whole point. A figure in kilometers would have been a meaningless avalanche of zeros, the kind of quantity the mind files at once under very large and forgets. Expressed in light-years, it spoke. 10 light-years meant that the light gathering in Bessel's heliometer had left 61 Cygni about a decade earlier and traveled, without pause, ever since. He was not seeing the star. He was seeing the star as it had been 10 years before, its image a decade stale by the time it reached the glass. The Hooke's promise that the nearest stars show you years-old light stopped being an image in 1838 and became a measured fact with a number on it. For the first time in the history of the species, a person could say how far away a star was and hand the figure to someone else to check. There is a deeper reason Bessel's geometric method mattered so much, and it points ahead to a problem the latter would hit again and again. You cannot read a star's distance off its brightness. A star looks bright in our sky for two quite different reasons that the eye cannot tell apart. It may be genuinely luminous, or it may simply be near. Some of the most dazzling stars in the night sky are blazing giants seen across enormous distances, while some of our closest stellar neighbors are so dim that the unaided eye cannot find them at all. Brightness alone is hopelessly ambiguous. The only way through, in Bessel's day, was the cold geometry of the triangle, which cares nothing for how a star shines and asks only how it shifts. That independence is exactly what made parallax trustworthy, and the day astronomers learned to read true brightness from a star's behavior, and so turn brightness itself into a yardstick, the latter would climb a great deal higher. But that breakthrough was most of a century away. Bessel was not working alone, and the human thread thickens here. In Russia, Wilhelm Struve was wrestling the bright star Vega toward an answer. From the southern hemisphere, Thomas Henderson had been measuring Alpha Centauri, which would prove to be the nearest star of all, just over 4 light-years off. Henderson, cautious and slow to publish, let Bessel reach print first with the cleaner result, but within the span of a year, 3 observers, attacking 3 different stars, had together shattered a barrier that had stood since antiquity. The dome that human perception drapes across the sky had been given, at last, a depth, measured, not imagined. The technique even minted its own unit, and the unit still carries its fingerprint. Astronomers defined the distance at which a star would show a parallax of exactly 1 second of arc and named it the parsec, a word welded together from parallax and second. 1 parsec is about 3¼ light years, and the nearest stars lie only a few parsecs from the Sun. Set that against the doorway model from before. With the Sun shrunk to a doorway and every planet scattered across a few kilometers of field, the next star is not at the field's far edge, but tens of thousands of kilometers away, more than once around the real Earth. Bessel's measurement is what poured a hard number into that gap. The Sun is a marble. Its nearest neighbor is another marble, several light years off, with nothing but vacuum stretched taut between them. And that spacing, exactly as we found among the planets, is not loneliness, but protection. Stars sit so far apart that close encounters are vanishingly rare, which is why each one can hold its own family of worlds steady for billions of years. But notice what the new unit quietly confesses. We did not measure the distance to 61 Cygni in kilometers and convert it into years for the sake of convenience. Out here, time is the natural ruler. The light year is not decoration on a distance. It is the honest shape of the distance, because distance and time have fused into a single thing. They fused because light, the fastest messenger there is not nearly fast enough to make these gaps feel small. It needs years to cross even the space between neighbors. That one fact, that the quickest thing in the universe is still painfully slow against the scale of the universe, governs far more than the choice of a unit. It governs what we can see, when we are allowed to see it, and whether we can ever reach it at all. To go further up the ladder, we have to reckon honestly with just how slow the fastest thing in existence really is. So how slow is the fastest thing there is? Put a number on it first. Light travels at very nearly 300,000 kilometers every second. By any human measure, this is an absurd speed. In the time it takes to say the word now, a beam of light could circle the Earth 7 times over. Nothing you have ever watched move offers the faintest comparison. A rifle bullet, a jet, a lightning strike are all, against light, effectively standing still. And yet the moment you carry this speed off the surface of the Earth, it stops feeling like a velocity and starts feeling like a crawl. We have been quietly collecting the evidence for that already. Light crosses to the moon in a little over a second. It takes 8 minutes to reach us from the Sun. It needs hours to span the outer solar system, which is why the people steering distant probes send a command and then wait half a day to hear that it was received. And it takes years, 10 of them, for Bessel's star to arrive from even the nearest suns. It is the same messenger every time. The only thing that changes is the size of the gap it must cross, and as the gaps climb the ladder, the delays climb with them. Second to minute, to hour, to year. Nor does the climb stop at the neighbors. Light from the far side of our own galaxy has been on its way for tens of thousands of years. Light from nearby galaxies has traveled for millions. Light from the most distant things our instruments can register has been crossing the void for most of the age of the universe, and is only arriving now. That light travels at any finite speed at all was itself a discovery, and a stubborn one, because in a room, across a field, even from horizon to horizon, light seems to arrive the instant it leaves. Galileo had tried to catch it out with lanterns, 2 people on distant hilltops, each uncovering a shuttered lamp the moment they saw the others, hoping to time the round trip. Light was far too quick for so crude a stopwatch, and he came away able to say only that its speed, if it was finite at all, was enormous. The real proof came in 1676, from a Danish astronomer named Ole Romer, who was carefully timing the eclipses of Io, one of Jupiter's moons, as it slipped into the planet's shadow. He noticed that the eclipses ran late when the Earth lay on the far side of its orbit from Jupiter, and early when it lay near, by as much as a quarter of an hour across the year. The moon's clockwork had not changed. The light-carrying news of each eclipse simply had farther to travel when the Earth was distant, and the extra distance cost it measurable time. From the size of that delay, and the width of the Earth's orbit, rumor showed that light moves at a great but finite speed. The same orbit that would later serve as Bessel's baseline for measuring distance had served a century and a half earlier, as the baseline that first caught light in the act of taking time. It would be one thing if this delay were merely a quirk of the particular light we happen to use, something a cleverer signal might outrun. It is not. The speed of light is not only the speed of light, it is the speed limit of the universe, the fastest rate at which any influence, any signal, any scrap of information can pass from one place to another. Nothing that carries news travels faster, not radio waves, not the pull of gravity, not any messenger known or imaginable. This is one of the most thoroughly tested statements in all of physics, and it has never once failed. It means the delay is not a temporary inconvenience waiting on better engineering. It is permanent. There is no faster bulletin on its way. The image of the star that left a decade ago is the freshest report the universe will ever issue. There is no more recent edition to be had, at any price, by anyone. The same ceiling caps not just our news, but any imaginable journey. Even a craft somehow able to travel at the speed of light itself would need years to reach the nearest star, and tens of thousands to cross the galaxy. The gaps are written in the one currency that cannot be cheated. The slowness of light and the vastness of space are, in the end, the same statement made twice. Sit with what that does to the sky overhead. Every point of light up there is showing you not how things are, but how they were, each by a different amount, set precisely by its distance. The moon as it was a second and a quarter ago. The sun of 8 minutes past. A nearby star as it stood when you were 10 years younger. A more distant one as it was before you were born. You are not looking out at the universe so much as looking down into it, into a stack of pasts, the most recent nearest to hand and the oldest furthest away, each layer's light stamped with the time it has spent in transit. What feels like a single flat picture of the heavens, taken in this instant, is nothing of the kind. It is an archive, sorted by depth, in which no two objects are showing you the same moment. There is something worth pausing on in that word, archive. Almost every other science gets to handle its subject. A chemist mixes the reagents. A biologist prods the cell. A geologist splits the rock open. Astronomy alone is forbidden all of this. The stars cannot be fetched, sampled, heated, or rerun. They sit unreachably far away and supremely indifferent, and the only thing they ever send us is light. Everything we know about the universe beyond the reach of our handful of probes has been read out of that incoming light and nothing else. Its color, its brightness, its faint shifts and flickers. We are not experimenters out here, but readers, and what we read is always old mail, posted long ago, by senders we can never write back to. The whole of cosmic astronomy is the art of extracting an entire universe from letters that arrive late and cannot be answered. And here is the consequence that will press harder the higher we climb. To see a thing is not to reach it, and out here, the two come apart entirely. When you see a star 10 light years away, the light in your eye is 10 years old. If that star were to change tonight, flare, collapse, even cease to exist, you would not learn of it for 10 years, because no news can outrun the light that carries it. For the most distant objects, the gap is not 10 years but billions, and the severance becomes total. We see such things only as they were in the deep past, while whatever they have become in the meantime stays hidden, their later light still somewhere out in the dark, not due to arrive for ages yet. Light binds us to the cosmos, but only as a one-way courier of old news. It lets us look without letting us touch, and it ensures that everything we look at late. We will come back to just how absolute that severance becomes, out at the limit of what can ever be seen. This is almost always told as a limitation, and in one sense it plainly is. We are sealed inside the present moment of our own small corner, allowed nothing but old letters from everywhere else. But the very same fact can be read the other way, and that second reading is what turned astronomy from stargazing into something far stranger and more powerful. If every distance is also a delay, then distance and time are not two separate things but one axis seen from two sides, and the depth of the sky is a depth in time. To look further out is not merely to look farther, it is to look earlier. The faintest, most distant light is also the oldest light, the nearest thing we will ever have to a direct view of the universe in its youth. The same slowness that keeps the stars forever beyond reach also makes the night sky the one instrument capable of seeing into the past, and the moment astronomers grasped that, they stopped apologizing for the delay and began to use it as their deepest telescope. Take the simplest version of the idea first, and let it build outward. Choose a distance, and you have chosen a date. Look at the moon, and you are looking a little over 1 second into the past. Look at the sun, and you are looking 8 minutes back. Look at Bessel's star, and you are looking 10 years back. Keep going, and the consequence becomes genuinely strange. The bright stars of any familiar constellation are not contemporaries at all. One may be showing you light that left a few decades ago, while the star apparently beside it is showing you light from 1,000 years ago. The two flung together on the dome only because they happen to lie along nearly the same line of sight. A constellation is not a group of neighboring stars. It is a chance alignment of different centuries, pressed flat by perspective into the illusion of a single picture. There is no shared now hanging in the night sky. There is only a fan of pasts, each object set at the depth its light has had to cross to reach you. You can witness this yourself, on a dark night, with no instrument whatsoever. The faint smudge of the nearest large galaxy to our own hangs in the autumn sky as a patch of dim, gray light. And that light is roughly 2.5 million years old. It left its galaxy before our own species existed, crossed the entire emptiness between two galaxies, and is only now arriving at the back of your eye. To look at that smudge is to look at a time before human history, before human beings of any kind, a direct and unmediated glimpse into the deep past, available to anyone who steps outdoors and knows where to turn their face. The oldest thing most people will ever see with their own eyes is not anything on Earth. It is that dim patch of light, older than the human story by a wide margin. Now hand the same principle to a great telescope and let it stare. In 1995, the director of the Hubble Space Telescope made a decision many of his colleagues thought reckless. He chose to aim the instrument at a tiny, apparently empty patch of sky, a speck holding no known bright star and no known galaxy, a scrap of seeming nothing, barely larger than a grain of sand held at arm's length, and to hold it there, quietly gathering light, for 10 days together. To many, this looked like pouring some of the most valuable observing time in the world down a drain. When the faint, slowly accumulated light was at last assembled into a single image, that empty speck turned out to contain several thousand galaxies, crowding away into the distance, the faintest of them so remote that their light had been crossing space for most of the age of the universe. The emptiness had been an illusion of impatience. There is no blank sky, there is only sky no one has yet stared at long enough. And here the timeline reveals its most disorienting property. Because greater distance means older light, the most distant galaxies in that image are not simply the farthest away. They are also the youngest, caught and held as they were when the universe itself was young. Look at the nearer galaxies in such a picture, and you see them roughly as they are in our own era. Large, settled, turning in graceful spirals and smooth ellipses. Look to the middle distance, and they begin to change. Smaller, rougher, more disorderly, lit with the harsh glare of furious star formation. Look to the very floor of the image, to the faintest reddened smears of all, and you are watching galaxies in the act of assembling themselves, ragged clumps of brand new stars from a time when the cosmos was only a small fraction of its present age. The depth of the field is a depth in time, and as the eye sinks through it, the universe grows visibly, measurably younger. A single long exposure of one patch of sky is, quite literally, a photograph of cosmic history, the recent foreground and the ancient background stacked together in the same frame. There is a subtle and powerful method buried in this. We can never watch a single galaxy grow up. Even the fastest changes out there unfold across hundreds of millions of years, far beyond any human or instrumental lifetime. We will only ever catch any one galaxy in a single frozen instant of its existence. But the timeline hands us a way around that limitation. Because every depth shows a different age of the universe. A deep image captures galaxies at every stage of development at once. Infants at the bottom, adolescents in the middle, mature systems near the top, and by sorting thousands of them by distance, astronomers can lay the stages in order and reconstruct the life story. None of them will sit still long enough to perform. It is the same trick a visitor from elsewhere might use to learn how humans age, not by following one person for 80 years, but by photographing a crowded square once and arranging the faces from youngest to oldest. The universe, sorted by depth, supplies the whole crowd in a single exposure. This is the quiet revolution folded inside the slowness of light. Astronomers never get to see the universe as it is. The as it is smeared across billions of years and permanently out of reach. Every region's present-day light still somewhere in transit and not due for ages. What they see instead is the universe's whole history, spread out before them all at once and sorted by distance. The present close at hand, the remote past far off, every era on display, at the same time, somewhere in the sky. To study the distant cosmos, then, is not to take a census of the present but to read a history. And the further a telescope reaches, the earlier the era it uncovers. Depth is the index of the archive. This is the promise made at the very start, now fully literal. The delay that keeps every distant thing stale is precisely what lets us watch the universe's youth directly, not reconstruct it from clues, but watch it in light that set out when that youth was the living present. But a history read by depth must have a bottom, and it is worth seeing why. If looking further out is the same as looking further back, then somewhere out there must lie the oldest light of all, the most distant thing it is possible to see, beyond which there is nothing earlier left to look at. Sink far enough through the deep field, and the galaxies do thin out and disappear, not because the telescope has failed, but because you have reached back to an era before the first galaxies had formed, a time with almost no bright sources to send any light at all. And beyond even that lies a barrier of a different kind, not a darkness, but a wall of light, a faint, even glow that fills the entire sky in every direction, the oldest light there is, released at a moment when the whole universe was young and hot and had not yet turned clear. We will reach that wall before we are done and read what is printed across it. For now it is enough to know that the archive has a final page, and that the same finite speed of light which sorts the sky into eras also guarantees both a first era we can see and a curtain hung just beyond it. All of this, the timeline, the deep field, the youngest galaxies banked at the bottom of the frame, has quietly carried us out of our own neighborhood and into the company of other galaxies, as though the leap from single stars to whole island systems of stars were no leap at all. It is a considerable leap, and we have skipped a vast structure to make it. Between Bessel's one measured star and that smudge of 2.5 million-year-old light lies something we have stepped straight over, the enormous wheel of several 100 billion stars that we ourselves are lodged inside, and to which every star you can see with the naked eye belongs. Before we can speak honestly about other galaxies, we have to confront our own, and with the peculiar difficulty of trying to map a city while standing in the middle of one of its streets. The difficulty announces itself the moment you try. We cannot step outside our galaxy and look back at it. We are inside it. We have always been inside it, and every map we possess of it has been drawn from within, by observers who can never reach the doorway to glance back through. To feel the problem properly, start with what the galaxy actually looks like from where we sit. On a genuinely dark night, far from any town, a pale band of light arches across the entire sky from one horizon to the other, faint, soft-edged, like a river of mist or a road paved with cloud. Every culture that ever looked up gave it a name and a story. A spilled path of milk, a celestial river, a road for the dead or the divine. For all of human history, it was a glowing smear with no resolved detail, and no one could say what it was made of. Then, in 1610, Galileo turned his new telescope on it, and the mist dissolved into what it had always secretly been: stars. Countless individual stars, too faint and too tightly crowded for the unaided eye to separate, smeared together by sheer number into a single soft glow. The band was not a cloud at all. It was a multitude, and we were inside it. The shape of that multitude can be read almost directly off the way it appears in the sky. Why should the stars form a band at all, rather than scatter evenly in every direction? Because we live inside a vast, flattened disk of them. Look along the plane of that disk, edge on from our position within it, and your line of sight runs through star behind star behind star, deeper and deeper, until they blur into the bright, dense river of the Milky Way. Turn your gaze instead up out of the plane, perpendicular to the disk, and your line of sight passes quickly through the thin layer of stars and out into near empty space beyond, and there, away from the band, the sky is dark, dusted with only the relatively few stars that happen to lie nearby. The band is nothing more exotic than the inside of a plate, seen by someone living inside the plate. From that single observation alone, you can deduce that you inhabit a flattened slab of stars and are looking out through its narrow dimension in some directions and its long dimension in others. William Herschel tried to turn this insight into an actual map in the 1780s by the punishing method of counting stars in hundreds of different directions and reasoning that he was seeing farther wherever the stars ran deeper. He arrived at a flattened, raggedly rounded form, broadly the right shape, though he placed the sun mistakenly near its center because the dust he had no way of seeing was quietly hiding the galaxy's true extent from him. His instinct was nonetheless exactly right. The structure of the galaxy is written in how its stars are distributed around us, and the whole task is to read that distribution without being fooled. Lay out the parts then, as we now understand them. The bright disk is the galaxy's defining feature, a slowly turning plate of several 100 billion stars, together with the gas and dust out of which fresh stars are still condensing, roughly 100,000 light-years across, but only a small fraction of that in thickness. Shrink it to the width of a dinner plate, and it would be no thicker than a few sheets of paper laid together. Within that disk, the stars are not spread smoothly, but gather along great sweeping spiral arms. It is worth being clear about what those arms are and are not. They are not solid objects, nor fixed pinwheel blades that the stars are glued to. They are moving regions where matter bunches up and star formation flares most fiercely, lit by brilliant, short-lived young stars that make the arms blaze out against the fainter disk between them. A spiral arm is closer to a traffic jam than to a structure, a place where stars and gas slow and pile up as they pass through, while individual stars drift in and out of it over time, much as cars crawl through a jam and then accelerate away while the jam itself stays put on the road. At the galaxy's center swells a denser, rounder bulge of mostly older stars, and buried in its very heart lies a black hole of some millions of times the sun's mass, a fact we will note in passing and leave undisturbed. Wrapped around the whole disk is a sparse, roughly spherical halo containing the galaxy's most ancient stars, many of them gathered into the dense, tight-packed globular clusters that swarm far above and below the plane on long looping orbits. Set a number against all this and the familiar vertigo returns at a new scale. 100,000 light-years means that light itself, which crossed to the moon in a second and reached us from the nearest star in years, needs a full 100,000 years simply to travel from one edge of our galaxy to the other. Several 100 billion stars wheel within it, and yet, for all that multitude, the disk is overwhelmingly empty. The stars are still separated, on average, by light-years apiece, just as the doorway and field model insisted, so that the crowded band of the Milky Way is, up close, almost entirely vacuum. If the solar system is a doorway and a field, the galaxy is a city of hundreds of billions of suns, and our entire solar system, sun, planets, the whole empty field of it, is a single grain of dust drifting down one of its quieter streets. Every star you have ever seen with the naked eye, every star in every constellation that has ever been named, is one of our immediate neighbors inside this one city. You have never once, with your unaided eye, seen a single individual star belonging to any other galaxy. Our address within the city, moreover, is thoroughly unremarkable. For a long time, it seemed natural to assume the sun sat somewhere near the center of things, as Herschel had supposed. In 1918, Harlow Shapley dismantled that comfortable idea by mapping the globular clusters of the halo and finding that they were not arranged around the sun at all, but around a point far off in the direction of the constellation Sagittarius, the true center of the galaxy, tens of thousands of light-years away from us. The sun, it emerged, sits far out toward the rim, roughly 2/3 of the way, from the center to the edge, tucked into a minor spur between two of the major arms. We do not live at the heart of our galaxy, we live in its suburbs, and we found this out only a century ago, nor are we sitting still out there. The entire disk turns, and the sun, carrying its planets with it, sweeps around the distant galactic center at well over 200 kilometers every second, a furious speed by any measure the Earth can offer. But the city is so unimaginably large that even at that pace, a single circuit of it takes something over 200 million years. The sun has completed only around 20 such laps in the whole of its existence. Since the last time it occupied precisely this point on its orbit, entire ages have risen and passed on Earth. The dinosaurs flourished and vanished within the span of roughly one galactic turn. Our galaxy keeps a clock so slow that the entire age of mammals amounts to a fraction of a single one of its revolutions. And here we collide squarely with the difficulty we began with. Everything just described, the disk, the arms, the bulge, the halo, the sun stranded 2/3 of the way out, we know without ever having seen any of it from the outside. No craft has come remotely near to leaving the galaxy to photograph it, and none will on any human timescale, since even at the speed of light, a journey to a vantage point high above the disk would take far longer than our species has so far existed. Every magnificent image of the Milky Way as a glowing spiral viewed from above is one of two things: a photograph of some other galaxy standing in for our own, or an artist's reconstruction, assembled from indirect evidence. We have never seen our galaxy's face. We have only ever seen it from the inside, edge on, peering through a haze of intervening stars and, worse still, through immense banks of obscuring dust that wall off the view toward the very center we most need to chart. To draw the city while standing in one of its fog-filled streets, astronomers had to invent ways of seeing that the human eye simply does not possess, and that meant learning to gather kinds of light the eye cannot register at all. The dust is the heart of the problem. Scattered between the stars, mixed all through the gas of the disk, drift enormous clouds of fine dust, grains of carbon, and silicate far smaller than specks of smoke, each one almost nothing in itself. But spread across thousands of light years, they gather into an opaque veil. To visible light, they are very nearly a wall. A grain of that size happens to be well matched to the wavelength of visible light, and so it absorbs and scatters that light with cruel efficiency, stripping it out of the beam before it can ever reach us. You can see the milder version of this effect with the naked eye. The dust does not block all colors equally but robs blue light first, so stars seen through it look redder than they truly are, reddened in the same way and for much the same reason as the setting sun. Look toward the crowded center of the galaxy in ordinary light, and you do not see the center at all. You see at best a few thousand light years into the disk before the piled-up dust chokes the view off completely. The galactic heart, tens of thousands of light years away, hides behind a wall of soot. For as long as astronomy possessed only visible light, the center of our own galaxy was simply out of reach, nearer than countless other galaxies we could photograph in perfect clarity, and yet utterly veiled. The way out lay in a simple fact about waves and obstacles. A wave sweeps cleanly around anything much smaller than its own wavelength, and is seriously blocked only by obstacles comparable to or larger than that wavelength. The dust grains are sized to block visible light, but radio waves, which are vastly longer, and infrared light, which is somewhat longer, stream straight past those grains, as though the dust were not there at all. The same fog that walls off the galactic center in visible light is almost perfectly transparent in radio and in the infrared. The grains have not gone anywhere. The longer waves simply do not register them. Build an eye that sees in those longer wavelengths, and the veil lifts. The most powerful of these new eyes reads a faint radio note given off by the most ordinary substance there is, hydrogen gas, which fills the space between the stars in staggering quantity. A hydrogen atom left to itself can sit in either of two almost identical internal states, and every so often it flips between them, shedding a tiny pulse of radio energy at one sharply defined wavelength, 21 centimeters. For any single atom, the flip is extraordinarily rare, something it might do once in millions of years. But there is so much hydrogen strewn across the galaxy that, summed over the whole disk, the 21-centimeter glow shines steadily and unmistakably, and it pours straight through the dust without the slightest hindrance. That cold hydrogen ought to emit at exactly this wavelength was predicted during the Second World War by a young Dutch astronomer, Hendrik van de Hulst, working under occupation with almost nothing to hand. The glow itself was first caught in 1951 by groups in the United States, the Netherlands, and Australia within months of one another. Overnight, astronomers possessed a way to map the gas of the entire galaxy. Dust be damned. The 21-centimeter line did far more than show where the gas lay. Because its true wavelength is known with great precision, any shift in the wavelength actually received betrays motion. Gas drifting toward us has its note crowded to a slightly shorter wavelength. Gas drifting away has it stretched a little longer, the same effect that drops the pitch of a siren as it passes and recedes. By reading these shifts all across the sky, astronomers could measure how fast each cloud of hydrogen was moving, and then, by folding in the overall rotation of the galaxy, estimate how far along each line of sight the cloud must lie. Cloud by cloud, velocity by velocity, the hidden gas sorted itself into a map, and out of that map rose the great spiral arms of the Milky Way, traced at last through the very dust that had hidden them since the beginning. The maneuver at the center of this, reading motion off the shift of a known wavelength, is one to keep firmly in mind. It will return, on an incomparably grander scale, the moment we turn to the galaxies beyond our own. Infrared light prized open the dusty center from the other side. Cool stars, warm dust, and crowded regions that give off little visible light all glow steadily in the infrared, and that glow, too, threads easily through the obscuring clouds. Infrared surveys, and later telescopes, carried above the atmosphere, finally exposed the galactic center that visible light could never penetrate. The dense central swarm of stars, the shape of the bulge, the whole hidden core of the city brought into view in light, lying just past the red edge of what the eye can register. The same reading of motion that traced the arms delivered, almost in passing, one of the strangest results in the history of astronomy. Track how fast stars and gas circle the galactic center at different distances out, and a reasonable expectation says the outermost ones ought to move more slowly, just as the outer planets dawdle around the sun while the inner ones race, because beyond the bulk of the visible mass, the gravitational grip should fade. They do not slow down. Measured with care, most famously by Vera Rubin and her collaborators in the 1970s, the outskirts of galaxies wheel round just as briskly as their inner regions, the rotation staying stubbornly flat far out into the darkness where scarcely any stars shine. There is only one way for gravity to swing those remote stars around so quickly. There must be a great deal more mass present than the glowing stars and gas can possibly account for, much of it arranged in a vast unseen halo wrapped around the bright disk. The galaxy weighs far more than it shines. What that extra, invisible mass actually is remains one of the genuinely open questions of physics, a puzzle we will leave for its own telling elsewhere. Here it enters only as something the measurements forced upon us, a weight read straight off the motions, an unseen majority given away by how fast the visible minority moves. Put all these instruments together and you have the answer to the puzzle we started from. We map the galaxy we can never leave, much as you might map a forest you can never climb above. Not by rising out of it for a clean overhead view, which is forbidden us, but by patiently sounding it from within, measuring the distance and the motion of every trunk within reach, in every kind of light that will carry the information, until the larger pattern resolves out of thousands upon thousands of local readings. Parallax pins down the nearby framework. The 21-centimeter line traces the gas and the arms straight through the dust. Infrared reaches the core, the Doppler shifts supply the motions and the rough distances. The flat rotation reveals the hidden mass. No single instrument sees the galaxy whole. The map is a mosaic, pieced together from many partial views in many kinds of light, an inferred portrait of a structure we will never once photograph from without. And it is, for all of that, a rigorous and trustworthy map, checked against itself from every side, each piece consistent with the rest. Notice, too, what every one of these instruments has in common. Not one of them is the eye. The radio dish, the infrared detector, the spectrograph that splits light to read its shifts, each is a sense the body does not come equipped with, deliberately built to reach where the eye fails, exactly as the parallax triangle was built to reach where stereo vision failed. The story of mapping the galaxy is the same story as the rest, a creature whose senses quit at the rooftops, manufacturing new senses, one after another, to grope its way toward distances it was never born able to feel. These same new eyes, turned outward, sharpened a question that had unsettled astronomers for 2 centuries. Scattered all across the sky, beyond the band of the Milky Way, hang faint spiral smudges of light, the one in the autumn sky among them. Were they small, nearby clouds of glowing gas, mere ornaments set within our own galaxy? Or were they separate galaxies in their own right, vast wheels of stars like ours, lying at staggering distances far outside it? Everything turned on how far away they were, and that was a distance no parallax could ever reach, for their shifts against the background were immeasurably small. To settle it, astronomers needed a new rung on the ladder, a way to gauge distances thousands of times beyond the grasp of geometry. That rung was about to be handed to them, quietly, by a woman patiently cataloging photographs of flickering stars, and it would enlarge the known universe beyond all recognition. Recall the problem parallax left unsolved. Geometry can reach only so far. Beyond a certain distance, a star's tiny seasonal wobble shrinks below anything an instrument can measure, and the triangle method simply runs out. To go further, astronomers needed something parallax could not give them, a way to know a star's true brightness without first knowing its distance. For if you knew how brightly a thing genuinely shone, its distance would fall out of how faint it merely appeared, through the same inverse square dimming that drains the sun's light across the solar system. A bulb of known wattage tells you its distance by how dim it looks. The entire difficulty is finding cosmic objects whose true output you can know in advance. Such objects are called standard candles, and the first one that worked was discovered not at a telescope, but at a desk, by someone forbidden to use the telescope at all. Her name was Henrietta Swan Leavitt, and she worked at the Harvard College Observatory in the early 1900s, as one of a group of women hired to measure and catalog the stars recorded on the observatory's photographic plates. They were called computers, because computing, careful, repetitive measurement and calculation was the work. They were paid little, given no say in what was studied, and as a rule not permitted to direct the great instruments whose output they spent their lives analyzing. Leavitt was assigned to catalog variable stars, stars whose brightness rises and falls, and she gave particular attention to a class of them, the Cepheids, which pulse with a steady rhythm, swelling and dimming, and swelling again over a cycle of days to weeks, as the whole star physically expands and contracts. She concentrated on Cepheids found within the small Magellanic Cloud, a faint companion patch of the southern sky, and in doing so she stumbled onto a piece of extraordinary good fortune folded into the problem. Because all the stars in that cloud lie at very nearly the same distance from us, the cloud being far off and compact, their apparent brightnesses could be compared directly with the usual confounding question of distance removed at a stroke. Any Cepheid that looked brighter than another in the cloud genuinely was brighter, not merely nearer, and when Leavitt arranged her Cepheids by the length of their pulsation cycle, a clean and unmistakable relationship emerged from the data. The longer a Cepheid takes to complete its cycle, the more luminous it truly is. Period predicts brightness. A slow pulse means a powerful star, a quick one, a feebler star, in a smooth and dependable law. It is worth being exact about what she had found, because it is one of the most important measuring tools in the history of science. The pulsation period of a Cepheid is something you can determine no matter how far away the star sits, simply by timing it, by watching the light rise and fall, and noting how long the cycle takes. Distance does not enter into a stopwatch reading, so Leavitt's law lets you take any Cepheid anywhere, time its pulse, and from that alone read off its true brightness. Compare that true brightness with how faint the star appears in the sky, and the inverse square law hands you the distance. She had turned a clock into a yardstick. A throbbing star had become a standard candle, and because Cepheids are giants, blazing thousands of times brighter than the sun, they are luminous enough to be picked out, not only across our own galaxy, but inside other galaxies entirely. Leavitt published the relationship in 1912, and then, as the structure of the work allowed, others took the tool she had forged and used it to remake the map of the universe. The law as she found it gave only relative distances. It had to be calibrated, anchored to a few nearby Cepheids whose distances could be fixed by other means, before it could yield distances in light years, and that calibrating work was done by others. She herself was moved on to different tasks and died in 1921, of cancer, still a poorly paid assistant. A few years later, a mathematician, not knowing she had died, began the process of nominating her for a Nobel Prize, which cannot be awarded after death. The single most consequential measuring rule in 20th century astronomy bears, by long habit, the names of the men who calibrated and applied it as readily as her own. It was her law. What that law made possible arrived within the decade, and it settled an argument that had split astronomy down the middle. The faint spiral smudges scattered across the sky, were they small clouds inside our own Milky Way, or vast separate galaxies far beyond it? The question had been debated head to head, with the greatest astronomers of the day lined up on both sides, and it could not be resolved because no one could measure how far away the spirals lay. The clash had even been staged formally in 1920 as a public confrontation now remembered as the Great Debate. On one side, Harlow Shapley, the same man who had correctly banished the sun to the galaxy's suburbs, argued that the Milky Way was essentially the entire universe and the spirals mere nearby clouds within it. On the other, Heber Curtis insisted they were distant island universes in their own right. Both marshaled the best evidence available, and the argument stayed deadlocked, because conviction was all either side could offer in place of a measured distance. Edwin Hubble settled it with Leavitt's candle. Working at Mount Wilson, with the finest telescope then in existence, its mirror 100 inches across, he photographed the Great Spiral in Andromeda, catalogued as M31, night after night, until in the swarming stars of its outer regions he caught what he was hunting, individual Cepheid variables, pulsing exactly as Leavitt's stars had pulsed. He timed their cycles, read off their true brightness from her law, compared it to how desperately faint they appeared, and calculated the distance. The answer was staggering. Andromeda lay far, far outside the Milky Way, hundreds of thousands of light years away, by his cautious first reckoning, and in truth several times farther still. There was no possibility it sat within our galaxy. It was a galaxy, a separate island of countless stars, complete in itself, adrift at an unbridgeable remove. On one of his plates, Hubble crossed out an earlier note and wrote a single triumphant word beside a star he had identified, a variable, and that one marked star, on that one plate, is fairly said to have enlarged the universe overnight. Our Milky Way, the whole island we had taken for the cosmos entire, was abruptly demoted to one island among an uncountable many. The smudges were galaxies, every one of them, strewn through a space vastly larger than anyone had been prepared to imagine. And here the faint patch from before comes fully into focus. That dim gray smear in the autumn sky, the oldest thing the naked eye can see, is Andromeda, not a cloud, not an ornament of our own galaxy, but an entire separate galaxy of several 100 billion stars, its light 2.5 million years old by the time it reaches you. When you find it on a dark night, you are looking with your own unaided eye across the gulf between galaxies, at a wheel of stars as great as our own. It is the farthest your bare senses will ever reach, and it is another Milky Way. Andromeda is also our nearest large neighbor, and the two of us are not alone. Together with a few dozen far smaller galaxies, the Milky Way and Andromeda form a loose, gravitationally bound flock called the Local Group, two grand spirals and a scattering of dwarfs, drifting and orbiting within their shared gravity. Most of the group's galaxies are faint and small. The two big spirals dominate it, and they are slowly falling toward each other, destined to meet and merge billions of years from now. This is the next rung up from the single galaxy. Galaxies, too, keep company, gathered into groups by gravity, the way stars are gathered into galaxies and planets into systems. The pattern of clustering repeats, level upon level. Hubble, though, did not stop at Andromeda. Having found his footing on Leavitt's rung, he pressed outward to galaxy after galaxy, measuring their distances, and as he did, he turned his attention to another quality of their light, the precise wavelengths of the features printed in it. There he met something he had not gone looking for, and could not at first explain. Almost every galaxy he examined had its known wavelengths shifted toward the red, as though the whole galaxy were sliding away from us. And the more distant the galaxy, the greater the shift, the faster the apparent flight. The same Doppler reading that had traced hydrogen through the dust of our own galaxy, now applied to whole islands of stars, was about to deliver the most unexpected fact about the universe anyone had ever uncovered. Take the bare fact on its own first, before any interpretation is laid on it. When Hubble and others measured the redshifts of galaxy after galaxy and set each one against that galaxy's distance, a startlingly simple pattern fell straight out of the numbers. The shift was not random. A galaxy twice as far away showed twice the shift. One 3 times as far, 3 times the shift. The recession speed read from the redshift was simply proportional to the distance. The farther the galaxy, the faster it appeared to flee, in a clean, straight-line relationship that held across galaxy after galaxy. The relation is usually attached to Hubble's name and to the year 1929 when he published it, but its meaning had been worked out 2 years earlier by a Belgian priest and physicist, Georges Lemaitre, who had derived from theory that an expanding universe would produce exactly this proportionality. He is now justly named alongside Hubble in the law. Observation and theory had arrived, by separate roads, at the same astonishing place. The obvious way to read the fact is that we sit at the center of a great outrush, every galaxy fleeing from us in particular, as though some vast explosion had flung them all outward from our position. That reading is wrong, and understanding why is the key to the entire picture. The galaxies are not, for the most part, hurtling away through space at all. Space itself is expanding, swelling between them, and carrying them apart, much as 2 dots painted on the skin of an inflating balloon are carried apart not by sliding across the rubber but by the rubber stretching beneath them. The redshift is therefore not the ordinary Doppler shift of an object speeding through a fixed void. It is light stretched in transit by the growth of the very space it is crossing. As the space the light travels through expands, the waves of that light are drawn out longer along with it, shifted toward the red by precisely the amount the universe has grown during the journey. This single change of interpretation lifts us out of the center, because an expanding space has no center at all. Picture again the dots on the swelling balloon. Every dot sees all the others drawing away from it, and the more distant dots receding faster, and yet no dot is the center of the expansion. On the stretching surface, there is simply no central point from which the rest retreat. Or picture a raisin loaf rising in a warm oven. As the dough swells, every raisin moves away from every other, and a raisin anywhere in the loaf would see its neighbors receding, the farthest fastest, with itself apparently sitting still at the middle of the retreat. Every galaxy in the universe sees exactly what we see, An astronomer in Andromeda, or in some galaxy a billion light-years off, would find the very same law, all others fleeing, the distant ones fastest, and would be just as tempted and just as mistaken to place themselves at the heart of it. There is no heart. There is no edge that the galaxies are flying into. There is only space, everywhere at once, growing larger. It is worth pausing on how violently this overturned the older picture. For all of history before it, the universe had been assumed to be static and eternal, a fixed stage, however vast, on which the stars simply were. Even Einstein, deriving the behavior of space and time, had assumed a changeless cosmos so confidently that he adjusted his own equations to keep it from moving, before the galaxy's flight forced everyone to abandon the assumption. The universe was not a fixed stage. It had a history. It was going somewhere, and it had come from somewhere. And that single realization turned cosmology, from a description of scenery, into the study of an unfolding event. An immediate and natural question arises, and answering it sharpens everything. If space is swelling everywhere, why do we not swell along with it? Why do the Earth, the solar system, our own bodies not stretch and grow? Why does the gap to Andromeda not widen, when Andromeda, in plain fact, is drifting toward us rather than away? Because the expansion is gentle, and anything held together by a force stronger than that gentle pull simply ignores it. Within an atom, the electrical forces that bind it are overwhelmingly stronger than the cosmic stretch. Within the solar system and the galaxy, gravity's grip is far tighter. Even the whole local group is bound firmly enough by its own gravity to hold itself together and refuse to be drawn apart, which is precisely why Andromeda falls toward us instead of receding. Only out on the largest scales, between galaxies and groups that are not bound to one another, does the expansion meet nothing to oppose it, and there it wins, carrying the unbound islands steadily apart. You are not expanding. The Earth is not expanding. The galaxy is not expanding. Only the open, ungoverned gulfs between distant, unbound galaxies are growing, and on those scales they grow without limit. Once you see the redshift as stretched space, rather than simple speed, the light from a distant galaxy becomes something far richer than a velocity gauge. It becomes a record of how much the universe has grown. If a galaxy's light arrives with its wavelengths doubled, stretched to twice the length they had when they set out, then space has doubled in size during the light's journey, and that galaxy must have emitted the light when the whole universe was half as large as it is today. Read a galaxy's redshift, and you read off directly how much smaller the universe was when its light departed. This deepens what the timeline of the sky already showed us. The distant galaxies are not merely older, caught in light that left long ago. They are caught in a younger and smaller universe, their stretched light carrying the exact measure of how much space has unfurled since they shone. Every remote galaxy hands us, written into the reddening of its light, a reading of the cosmic expansion at the very moment it was bright. The most distant galaxies yet found drive the point home. Their light reaches us stretched, not by half again, but many times over, so far drawn out that what left them as ordinary starlight arrives as infrared, having traveled since an era when the entire universe was less than a tenth of its present size, crowded and young. To measure such a redshift is to measure, with real precision, how much all of space has swollen across most of cosmic history. The faint reddened smudges at the floor of the deep field and the stretched light of the expansion are the same fact, seen twice. And a universe that expands has a history it cannot escape. If everything unbound is drawing apart now, then everything was once closer together. Wind the film backward, and the galaxies crowd inward, the space between them contracts, and the entire contents of the cosmos pack into an ever smaller, ever denser volume. Run the rewind far enough, and you reach a state in which all the matter and energy we can now see was crushed into a region unimaginably hot and dense. No galaxies, no stars, not even atoms, only a searing, near-uniform fire filling a tiny and swiftly swelling space. Lemaitre glimpsed this consequence early, and spoke of the universe beginning from what he called a primeval atom. The idea later picked up the half-mocking nickname by which everyone now knows it. The crucial point, for us, is plainer than any of its names. If the universe really did expand out of a hot, dense beginning, then that beginning ought to have left a trace, a flash of light from the moment the fire first cleared, set loose long ago and still traveling, still arriving. Even now, we have already brushed against the rumor of that light, as the wall standing at the very bottom of the sky's timeline. The expansion, is what tells us the wall must be there to find. But expansion is only half of what rules the largest scales, and left to itself it would smear the universe into a smooth, ever-thinning haze. The universe is not smooth, as astronomers used the redshift distance relation to place galaxies not merely in speed, but in three-dimensional position, sorting them near and far, mapping them through the real depth of space. The galaxies did not reveal themselves as sprinkled evenly through the growing void. They were gathered, strung together, pulled by gravity into a vast and intricate architecture that the smooth stretch of expansion could never have built on its own. To see that architecture, and to understand how it grew out of a nearly featureless beginning, we have to look closely at how the galaxies are arranged. The mapping began in earnest in the 1980s, and it began with an expectation that turned out to be wrong. When astronomers first set out to chart galaxies in all three dimensions, not merely their positions on the sky, which had been cataloged for a century, but their distances, supplied at last by the redshift, many of them expected to find the galaxies scattered fairly evenly through space, a more or less uniform sprinkling, thinning gently with distance. At the Harvard-Smithsonian Center for Astrophysics, Margaret Geller, John Huchra, and their colleagues set about measuring the redshifts of every galaxy in a long, narrow slice of sky, building up a true map of where those galaxies sat in depth, rather than merely where they fell on the dome. What appeared on the chart was nothing like an even sprinkle. It was structure, galaxies strung into long chains and arcs, gathered into dense clumps, and bordering great rounded gaps in which almost no galaxies lay at all. One of their early slices traced out a shape so striking that it was nicknamed for the stick figure it seemed to draw, its limbs sketched by the galaxies and its body by the emptiness between them. The universe, on the largest scales anyone had yet mapped, was not smooth. It was patterned, and patterned far more elaborately than anyone had thought. Later surveys, mapping not thousands of galaxies but millions across enormous volumes of space, confirmed the pattern and gave it its name, the cosmic web. Galaxies are arranged through space rather as droplets of water are caught on a vast three-dimensional cobweb. At the densest points, the nodes where many threads meet, sit great clusters of galaxies, hundreds or even thousands of galaxies, held together by their mutual gravity in a single swarm. Out of these nodes run filaments, long bridges and ropes of galaxies strung from cluster to cluster, some of them stretching for hundreds of millions of light years and ranking among the largest structures known to exist. Broad, thin sheets of galaxies span the gaps between the filaments. And wound all through the network, enclosed by its threads and walls, lie the voids, immense rounded regions, tens of millions of light years across, almost empty of bright galaxies, the hollows around which the whole filigree is wrapped. The matter of the universe is not spread evenly like a fog. It is drawn out into a network of dense thread and empty hollow, resembling nothing so much as a sponge, all connected wall and connected cavity, or the foam left clinging when most of a bath has drained away. It is worth noticing that the lesson of the doorway and the field has now returned at the largest scale there is. Most of the volume of the cosmic web is void. The galaxies, for all their grandeur, cling to the thin threads and walls, while the great rounded hollows, empty, dark, enormous, take up the overwhelming majority of the space. At every level we have climbed, the same proportion has held. A little matter, an ocean of emptiness. Planets are specks in an empty solar system. Stars are specks in an empty galaxy. Galaxies are specks strung on the empty web. Emptiness is not a failure of the universe to fill itself. It is the universe's principal ingredient, at every scale from the doorway to the web, and the matter is only the rare, bright tracing on an overwhelmingly dark and open ground. How does a nearly smooth beginning give rise to so intricate an architecture? The answer is gravity, working with endless patience as an amplifier of the faintest differences. Recall the hot, dense early universe that the expansion implies when run backward. That early state was very nearly uniform, but not perfectly so. Across it ran minuscule variations in density, regions a shade denser and a shade thinner than the average, the unevenness amounting to only about 1 part in 100,000. The barest whisper of lumpiness on an almost featureless sea. Gravity seized that whisper and ran. A region slightly denser than its surroundings pulls a little harder, gathering in nearby matter. Grown denser still, it pulls harder yet, gathering more. A runaway process in which the already rich grow richer. Across billions of years, gravity drained matter steadily out of the slightly emptier regions and heaped it into the slightly fuller ones, deepening those faint primordial ripples into the stark contrast we map today. Matter swept almost wholly out of the voids and piled high into the clusters and threads that wall them. The web is nothing more than the early universe's faint unevenness, grown enormous. The clusters mark where the seeds were densest. The voids mark where they were sparsest. The entire structure is the amplified, visible record of how very slightly lumpy the cosmos was at its start. We cannot watch this growth happen. It unfolds across billions of years, and we are back against the limit that no galaxy will hold still long enough to be filmed. So we do the next best thing, and build the universe inside a computer. Feed in the early conditions as we have actually measured them. A nearly uniform spread of matter freckled with tiny density seeds, the full mixture of ordinary matter, and the far greater unseen mass whose gravity dominates the whole, and the steady stretch of the expansion, and then let simulated gravity act, compressing billions of years of evolution into a calculation. What grows in the machine is a cosmic web, filaments knotting into clusters, sheets drawn between them, voids opening in the spaces, a structure strikingly, persuasively, like the real maps drawn from the real surveys. These are among the most demanding calculations ever attempted, tracking the gravitational pull of billions of parcels of matter on one another across the simulated lifetime of a universe. They are, in effect, another built instrument, a way of running an experiment on a cosmos we are otherwise forbidden to touch. The unseen mass does most of the labor, assembling first into an invisible scaffold of threads and knots, into which the ordinary luminous matter then drains and settles, lighting up the framework with galaxies we can see. When the simulated web and the measured web agree so closely in their threads and nodes and hollows, it is powerful evidence that we have genuinely understood how the structure formed, from seed to web, by gravity alone, across the lifetime of the universe. Step back now and take in what has happened. The cosmic web is the single largest pattern in the universe, and it was wholly invisible until measurement assembled it. No eye perceives it. No single photograph contains it. It exists, for us, only as the product of the entire ladder of distance. Every rung, from Bessel's parallax through Leavitt's candles to Hubble's redshift, was in the end a step toward placing galaxies in true three-dimensional space, and only when millions of them had at last been placed did this architecture rise out of the data. The web is the cumulative payoff of the whole measuring enterprise, the shape that appears once you have learned to locate things you can never reach. And it is the great bridge across cosmic history, the faint seeds of the early fire, drawn out by gravity into the very threads and nodes we now inhabit. We do not drift in a random scattering of galaxies. We live on one strand of a structure that grew, over billions of years, out of a whisper of unevenness in the newborn universe. Our own address within that structure is, predictably by now, unremarkable. The local group sits in a fairly ordinary reach of the web, out on its quieter strands, with the nearest truly great cluster of galaxies, the Virgo cluster, lying well off in the distance, a far richer knot than anything we belong to. We are not at a node. We are out on the threads, exactly as we are out in the suburbs of our own galaxy and out toward the rim of our own solar system. At every level, the same verdict has come back, again and again. Not the center, not the densest point, not anywhere special, only a typical place in a vast and patterned whole. The same conclusion the expanding universe delivered when it refused us a center, and the galaxy delivered when it banished us to the suburbs. And yet the web, for all its reach, is not endless to our eyes, not because it comes to a stop, but because our view of it does. The galaxy maps grow sparse and then fail at a certain distance, and they fail for the very reason that has shadowed every step of this long ascent. Light is finite, and the universe is only so old. Beyond a certain remove, the light of the galaxies has simply not had time to reach us since the beginning of everything. The web assuredly continues out there, thread and node and hollow, on, but we cannot see it, and in a strange and precise sense we never will. There is a horizon to the observable universe, a true edge to what can ever be seen, and it is the last and strangest consequence of the slowness of light. Start from the two facts that together make the horizon, both of them already in hand. The universe has a finite age. A little under 14 billion years have passed since the expansion began, something close to 13.8 billion. And light has a finite speed. Put those two together and a limit appears at once. Light can only have reached us from places near enough that its light has had time to cross the intervening gap since the beginning of everything. From anything farther, no light has yet arrived at all, because the universe has simply not existed long enough for the journey to be completed. That boundary, the greatest distance from which light could have reached us in the age of the universe, is the horizon of the observable universe. Everything within it is, in principle, available to our sight. Everything beyond it is not, and never has been. It is essential to be clear about what this horizon is and is not, because the word invites a misunderstanding. It is not an edge of the universe, not a wall where space stops, not a shore where matter runs out. There is every reason to believe the universe continues far past it, the cosmic web running on, thread and node and void, quite possibly without end. The horizon is an edge only of our seeing. It marks the farthest that light has so far been able to reach us from, and nothing more. It is precisely like the horizon at sea, which is not the edge of the ocean, but only the limit of how far the eye can follow the water before the curve of the world conceals the rest. Sail toward it, and it retreats before you. The ocean was always there beyond it. The cosmic horizon is the same in kind, a limit of sight, never a boundary of the thing seen. And like the horizon at sea, it is centered on the observer. We sit at the very middle of our observable universe, but so does every other observer sit at the middle of theirs. A horizon is not a feature of the cosmos at all. It is a relationship between a viewer and the speed of light, and every viewer carries their own. An astronomer in some far galaxy possesses an observable universe, centered on themselves, overlapping ours, but not identical to it, reaching to regions we shall never see, and missing regions we see easily. There is no privileged center here, only the plain fact that each of us stands at the heart of our own sphere of arrived light, exactly as the no-center logic of the expansion already insisted there could be no special place. One might naturally expect the horizon to lie a little under 14 billion light-years away, given that the universe is a little under 14 billion years old. In fact, it lies far more distant, and the reason is the expansion. The light from the most remote things we can see set out near the beginning, when their sources were comparatively close to us. But across the billions of years that light spent traveling inward, the space it was crossing kept swelling, carrying those sources steadily farther away even as their old light continued on toward us. So the sources whose ancient light is only now arriving have been swept, in the meantime, to a present distance of some 46 billion light-years. The observable universe is a sphere of roughly that radius drawn around us, far broader across than its age in light-years alone would imply, precisely because space refused to sit still while the light was in flight. It is worth holding the strangeness of that for a moment. We can state the size of the observable universe and count what it holds. Something like 2 trillion galaxies lie within that sphere, each an island of hundreds of billions of stars, all of them within the reach of our instruments in principle, all of them rungs the ladder has in some fashion touched. The whole universe may well be infinite, but the part we can ever see is finite, bounded, and measurable, a definite sphere of definite contents, with us at its center by the accident of being the ones doing the looking. Here the thread first opened long ago, that to see a thing is not to reach it, arrives at its final and strangest form. We have already found that the light we receive is always old, that we look without touching. The horizon sharpens this into something close to absolute. Because the expansion carries distant things away, there are galaxies whose light we can see at this very moment, whose images hang in our deepest photographs, that we could never reach, even if we set out toward them at the speed of light and traveled forever, because the space between us and them is lengthening faster than any signal could ever close it. We see them, we can never go to them, we cannot even send a message that would arrive. Sight reaches them, and nothing else ever will. And the severance cuts the other way as well. The expansion shows no sign of slowing. If anything, it is quickening, and as it bears the distant galaxies away, their light comes to us ever more stretched and ever fainter, until, in the far future galaxies that are plainly visible now, will have their light drawn out beyond all detection, and will slip silently past the horizon, winking out of our sky not because they have gone anywhere, but because the space between us has outrun their light. The observable universe is, very slowly, emptying. What we can see now is close to the most we will ever see. The window, measured across cosmic time, is quietly closing. There is a sobering corollary folded into that, and it sharpens what it means to be looking now. Far in the future, After the galaxies beyond our own group have all receded past the horizon and vanished, and after the Milky Way and Andromeda have long since merged into a single island of stars, any astronomers who arise then will look out and see only their own galaxy, adrift in a black and apparently empty sky. There will be no external galaxies to find, no redshifts to measure, no flight of the galaxies to reveal the expansion, no trace left of the early fire. Every clue that disclosed the expanding, evolving universe to us will have been carried out of sight. They could not, from observation alone, learn any of what we have just climbed through. We happen to live in an era when the cosmos is still legible, when the evidence of its history and its growth still hangs in our sky waiting to be read. That legibility is itself a fleeting condition. The ladder can be climbed because we are climbing it at the right moment. There is one more thing to say about the horizon, and it carries us back to a promise made early on. As we look outward toward the limit, the galaxies thin and dim, because we are looking back toward a time before galaxies had yet formed. But the view does not merely fade to black. Just within the ultimate limit of sight lies the wall of light we have now circled twice, a faint, even glow that fills the entire sky in every direction, the oldest light in the universe. It is the true visual edge of the observable cosmos, and not because nothing lies beyond it. It is the edge because beyond it the universe was opaque. In its first era, the cosmos was so hot and dense that light could not travel freely at all, but was trapped, scattering endlessly among the crowded particles like sunlight, hopelessly lost inside fog. We cannot see past that wall, not only because light from beyond has had no time to reach us, but because before that moment there was no clear light to send. The horizon of our seeing turns out to be this glowing surface, the boundary where the young universe first cleared and let its light run free. So the grandest possible view of the cosmos closes not on an empty edge but on a wall of ancient light, and we find ourselves sealed inside a sphere of our own reachable past, free to look out across the entire web of galaxies to a glowing boundary, and not one step further. It is the lesson of the 8-minute sun carried to its uttermost limit. The universe hands us light and withholds itself, lets us see almost everything and reach almost nothing, and rings us round at last with the oldest light there is. But that light is far more than the edge of our seeing. It is a message, arguably the single most important image in all of cosmology, and it carries, printed across it, the imprint of the universe as it was at the very instant it became visible. It is the last rung on the ladder, and the oldest, and it is time at last to read what is written there. The wall is the cosmic microwave background, and to read it we must return one last time to the hot, dense beginning the expansion forced upon us. Run the universe backward, and it grows hotter and denser. Follow it forward from there, and, for its first several 100,000 years, it was a furnace. At those temperatures, matter could not hold itself together into atoms. Electrons were torn loose from nuclei and roamed free, and a sea of free electrons is ruinous to light. A photon trying to cross it is scattered almost at once, knocked off its path again and again and again, unable to travel in a straight line for any real distance. The early universe was therefore opaque, not dark, but blindingly bright and uniformly foggy, a glowing plasma in which light was trapped, forever bounced, never free to go anywhere. Then, as space expanded, the fire cooled, and at a temperature of around 3,000 degrees, something decisive occurred. It grew cool enough for electrons and nuclei to settle together into stable, neutral atoms. The free electrons vanished into those atoms almost all at once, and with them gone, the fog lifted. Light could suddenly stream across space in straight, unimpeded lines. The universe turned transparent, and transparent it has remained ever since. This clearing happened when the universe was about 400,000 years old. The light set free at that instant, the glow of the cooling fire, released the moment it could finally travel, has been crossing space from then until now, for very nearly the whole age of the universe. It is the oldest light there is, the first light ever able to travel freely, and it reaches us from the surface where the fog lifted, in every direction we care to look. That surface is the wall. It is less a place than a time, the moment of clearing, glimpsed at the far edge of our sight in whichever direction we turn, because in every direction the light from that moment is only now arriving from far enough away. When it was released, that light was a fierce radiance, the glow of matter at thousands of degrees, shining invisible and infrared light. But it has traveled through expanding space for 13.5 billion years, and the same stretching that reddens the galaxies has drawn this light out far more, by a factor of about 1,000, lengthening its waves 1,000-fold and cooling the glow from thousands of degrees down to a little under 3 degrees above absolute zero. What set out as a brilliant fire arrives, after that immense stretch, as a whisper of microwaves, a faint hiss of cold radiation filling the entire sky, very nearly the same in every direction, the red-shifted echo of the universe's first free light. The relic fire is still here, all around us, cooled by the expansion straight into the microwave band. And that, exactly, is where it was found. It was found, fittingly, for everything this has been, by two people who were not looking for it, and at first, devoutly wished it would go away. In 1965, Arno Penzias and Robert Wilson, working at Bell Laboratories with an exquisitely sensitive horn-shaped antenna, were trying to make careful radio measurements of the sky, and they were being thwarted by a persistent faint hiss of microwave noise they simply could not eliminate. It came from every direction equally, by day and by night, season upon season, never varying in the slightest. They hunted the source with great care. They found that a pair of pigeons had nested in the throat of the great horn, and they cleared the birds out and scrubbed away the droppings the birds had left coating the inside, a substance Penzias would later describe, dryly, as a white dielectric material. Still, the hiss remained, uniform and inescapable. Meanwhile, only a short distance away at Princeton, a group led by Robert Dicke had reasoned that a hot early universe ought to have left behind precisely such a relic glow, now cooled into the microwave band, and had begun building an instrument to go looking for it. When the two groups were finally put in contact, the meaning of the stubborn hiss became clear in an instant. Penzias and Wilson had not found noise. They had found the oldest light in the universe, the relic of the hot beginning, picked up by accident as an annoyance they had spent the better part of a year trying to scrub away. The single most important image in all of cosmology was first detected as static that someone wanted gone. The discovery settled a long argument. A universe that began hot and dense should glow with exactly this relic radiation. A universe that had always looked roughly as it does now had no reason to glow at all. The microwave background was the decisive evidence that the cosmos genuinely did expand out of a hot, dense beginning, just as winding the expansion backward had implied it must. It is, quite literally, a photograph of the universe at 400,000 years old, the youngest the cosmos can ever be seen, the baby picture of all things, the final page of the sky's archive that we promised, early on, we would eventually reach. And reach it we have. Then the baby picture was examined more closely, and it yielded its deepest secret. The glow is astonishingly smooth, the same temperature across the whole sky to about 1 part in 100,000, a uniformity that is itself a wonder, since regions on opposite sides of the sky, which have never in the history of the universe been in contact, somehow shine at the same temperature to that fantastic precision. But it is not perfectly smooth. Mapped with enough care, the background reveals minuscule variations, patches very slightly hotter and very slightly cooler than the average, the differences amounting to just that 1 part in 100,000. Those faint ripples are the most important markings ever measured, because they are the density seeds themselves, photographed directly. The slightly hotter and cooler spots trace the regions of the early universe that were very slightly denser and very slightly thinner, the whisper of lumpiness out of which, we said, gravity would build absolutely everything. Here it is, caught at 400,000 years old, before gravity had yet done its work, the blueprint laid bare. Those very ripples, amplified by gravity across billions of years, grew into the cosmic web. Every cluster, every filament, every void, every galaxy, the Milky Way and Andromeda, and the very ground beneath your feet, all included. The map of the newborn universe's faint unevenness and the map of the grown cosmic structure are the same pattern, photographed once when young and once when old. The baby picture holds in seed the entire architecture we now live inside. Reading that pattern finely enough took a generation of instruments carried above the atmosphere. In 1992, a satellite called COBE first detected the ripples, proving the seeds were really there. Its leaders were honored with a Nobel Prize for the result. Later missions, WMAP and then Planck, mapped the ripples across the whole sky in extraordinary detail, measuring the precise sizes and spacings of the hotter and cooler patches. And from the exact statistics of those ripples, how large they are, how they cluster, which scales they favor, astronomers could read off the vital measurements of the entire universe, its age of 13.8 billion years, the proportions of ordinary matter, and of the far greater unseen mass, the overall geometry of space itself. The baby picture, measured carefully enough, turned out to encode the universe's full set of vital statistics. The faintest markings on the oldest light became the most precise rulers in all of cosmology. It is worth pausing on the sheer audacity of what that represents. We possess a measured photograph of the entire universe as it was at 400,000 years old, and by reading temperature differences across it smaller than 0.1%, we have weighed the cosmos, dated it, and charted its composition. And the chain of hands that made this possible runs unbroken through everything we have followed. Bessel, who first turned a star's faint wobble into a distance. Leavitt, who turned a pulsing star into a yardstick. Hubble, who used her yardstick to prove the galaxies external, and then caught them in flight. Lemaitre, who read an expanding universe in the equations. Rubin, who weighed the unseen mass by its pull. Penzias and Wilson, who stumbled on the first light while trying to be rid of it, and the teams behind the satellites who mapped its faintest ripples. Each handed the next a rung. No one of them saw the whole ladder. Together they built it from the rooftops to the edge of time. Stand back now and take in the whole shape of the climb. We began with light that was 8 minutes old and could not be felt as a distance at all. We end with light that is 13.5 billion years old, carrying the imprint of the universe's first clear instant and the seeds of every structure that has formed since. The same finite speed of light that turned every distance into a delay, that kept the stars forever beyond reach, is precisely what laid the universe's entire history open to us, oldest light at the bottom, and handed us a direct photograph of the beginning. The apparent curse, that we can only ever see old light, was the greatest gift measurement has ever been given. And yet none of it, not the baby picture, not the Webb, not the redshift, not the first measured star, was ever seen with the eye. Every last piece of it was caught by an instrument built to reach where the human senses fail. It is on those instruments, and on the long, stubborn effort to build new senses for a universe we were never equipped to perceive, that this whole story deserves to close. Every rung we have climbed was, at bottom, an instrument, a device for reaching where the body cannot. So let the story end on the instruments themselves and on what they truly are. A telescope, for all the sophistication later piled onto it, does at heart just two simple things, and both are ways of outdoing the eye. First, it gathers light. The pupil of your eye is a small opening, a few millimeters across, able to collect only the thin trickle of light that falls on that tiny area. A faint, distant source sends too few particles of light through it to register, and so remains invisible. A telescope replaces that small opening with a great mirror or lens, often meters across, gathering light over an area many thousands of times larger and funneling it all down to a single focus. The more light you can collect, the fainter the thing you can detect. And because the faintest things are the most distant, and the most distant are the oldest, a larger telescope is quite literally a deeper look into the past. Second, a telescope resolves finer detail than the eye can manage, splitting apart what the naked eye blurs into one. Galileo's little tube, no better than a child's toy by modern standards, was already enough to dissolve the Milky Way into individual stars and to catch moons circling Jupiter. The giant mirrors that came after turned faint smudges into spiral galaxies and let Hubble pick out his single pulsing star in Andromeda. Every increase in a telescope's size has been an increase in its reach, outward in space and backward in time at once. But the eye, and the ordinary telescope that merely extends it, are sensitive to only a narrow band of light, the slender range we call visible, a tiny window in an enormous spectrum. The universe pours out light far outside that window, and each kind reveals what the others conceal. We have already watched radio waves thread through the dust to map our own galaxy. Beyond them lies infrared, which shows the warm, the hidden, and the very distant. Ultraviolet, which picks out the hottest young stars. And X-rays and gamma rays, which betray the most violent events there are, the searing gas, and the great cataclysms. Most of these never reach the ground at all, because the same atmosphere that lets visible light through is a wall to nearly all the rest, which is why so much of modern astronomy has had to be lifted above the air, carried on satellites, and orbiting observatories that open each of these windows in turn. To take in the universe whole, We have grown an entire array of new eyes, one for each band of light, most of them blind to what we see, and seeing what we are blind to, and we have learned to lay their separate views together into a single understanding. The same patch of sky is a different world in each of them. Serene and star-strewn to the visible eye, it seethes with glowing gas in the infrared, blazes with violence in X-rays, and glows from edge to edge with the oldest light of all in the microwave. There is no single true picture of the universe, only the sum of all these views, each a real face of the same thing, none of them the whole. We have learned, too, to build single eyes of monstrous size by joining many smaller ones into one. Link a field of separate radio dishes together, combine their signals with enough care, and they behave as a single instrument as wide as the distance between them. Dishes spread across a continent or around the whole planet can be made to act as one telescope effectively the size of the Earth, sharp enough to tease out staggeringly fine detail. The reach of our built senses is no longer set by how large a single mirror we can pour and grind, but by how far apart we can place the pieces and still bind their light into one. It is worth being honest about what emerges from the far end of all this, because the glorious images of the cosmos that fill our screens are not photographs in the everyday sense, not scenes caught whole through a viewfinder. They are built, patiently, out of counted light. A modern detector does not so much take a picture as tally individual particles of light, registering them one at a time as they trickle in, accumulating the count over minutes, hours, or for the very faintest fields whole days, until enough have arrived to form a trustworthy measurement. Those counts are numbers, a vast grid of them, a brightness recorded at every point, and from that grid, an image is assembled. Where the light was of a kind the eye cannot see, radio or infrared or X-ray, its wavelengths are mapped onto visible colors we can register, so that the invisible is turned into something the eye can read. The colors in such an image are not lies, but translations, a faithful code that renders inhuman light into a picture a human can take in at a glance. And the light is split, as well, into its spectrum, spread into its component wavelengths, where the bright and dark lines printed across it disclose what a distant thing is made of, how hot it burns, how fast it travels, and how far its light has been stretched along the way. This is the final form of a truth we met long ago. Out here we are not viewers but readers, and every image of the deep universe is less a snapshot than a careful reading, rendered back into sight for eyes that could never have caught it raw. Set the two ends of this story side by side. At one end stands a single man at Königsberg, bent over a split-lens telescope through the winters of the 1830s, teasing out the minute wobble of one faint star to win the first true distance to anything beyond the solar system. At the other stand thousands of people across the world, building and launching and steering the satellites that map the oldest light in the universe across the whole sky, and read the makeup of the cosmos from its faintest ripples. Between those 2 points lies every instrument we have spoken of, and they are all, in the end, the same act repeated and enlarged. A creature whose senses give out at the rooftops, refusing to accept the limit, building out of glass and metal and arithmetic and a great deal of stubbornness, the new senses it was not born with. We did not grow eyes that could reach the stars. We made them. Return, at the very last, to where this began, to the two facts pressed together inside the feeling of vastness. One was the genuine, overwhelming scale of the universe, and that we have not altered in the slightest. The distances are as real and as enormous as they ever were, and no instrument shrinks them by a single kilometer. The other was the limit of the observer, the perceptual system that quits at the rooftops and files the entire sky under a single label, far beyond reach. That limit we could not cut out of ourselves. Every clear night, the eye still fails at the stars exactly as it always has, still drapes its flat dome overhead as though nothing had been learned. But we did the thing the eye could not do for itself. We measured what it could only gape at. The vastness is still there, and still felt. But now, alongside the helpless awe, there sits knowledge. The distance is named, the ages counted, the structure mapped, the beginning itself photographed and read. And that knowledge does not diminish the wonder, it changes its character. The awe of the unmeasured is a kind of helplessness, a standing back before something too large to hold. The awe of the measured is something better earned, the awe of knowing, precisely, how far the nearest star lies and how old its light is, and feeling the scale not collapse under the knowing but open wider, because now you grasp what the number truly means. If you enjoyed this exploration of how we came to measure a universe we were never built to perceive, a like or a subscribe helps us continue making them. Think back, one final time, to the flat ceiling the mind hangs above the night sky, the dome it improvises the moment its depth cues fail, every star pinned to the same dark surface, at the same unknowable remove. That ceiling was never real. It was the shape of our own blindness, drawn across the heavens. And rung by rung, measurement by measurement, from the bounce of radar off Venus, to the wobble of Bessel's lonely star, to the stretched light of the fleeing galaxies, to the faint hiss of the oldest fire, we have lifted it away. Where the eye saw a flat lid hung at one distance, we have opened a depth that runs unbroken from the moon a single second away to a glowing wall 13 billion years deep, every star and galaxy and filament set at last in its true place along the way. The ceiling has become a cathedral, and we are still walking into it, still measuring, still reading the light as it arrives. We were never able to feel how far it all reaches, but we have learned, at last, to know. The universe still has plenty left to reveal, and we will be following it as it does.